And let's do another couple of examples. I want to look at a video clip. This is from Big Buck Bunny. Big Buck Bunny is this open source movie from the Peach Open Movie Project. You can find the full length film on YouTube or at this website. But it's about this sort of overgrown, naive, innocent bunny who's being bullied by these three other creatures. And in this scene, he exacts his revenge on this flying squirrel creature. I want you to, as we watch this, I want you to think about the two instances of free fall, that is an object falling from a certain height to the ground, and how those two instances are different, how the information that we have in the clip is different for each of them. And then we'll approach each problem from a different way. So you can go and watch the clip. We're going to watch it in its entirety, and you can get it by clicking right here. So go ahead and watch it. All right, so in the movie, we have two instances of free fall. The first one is this peach that falls from a tree. So a little picture here. I had a peach, or it sort of looked like an apple, but it's the Peach Open Movie Project, so I know it's a peach. And it falls down in that distance. Now, in this case, we don't know the time because this occurred in slow motion. So we don't know what the time is for the free fall. However, we can estimate what is the distance that it falls. This was a pretty tall tree. I'm going to say that the change in y was about 20 meters. Actually, let me go back and I'm going to fix that. We want to, when we're defining these, we're going to define our positions as our initial position. So I'm going to call this y0, and that's equal to 0. And then down here at the bottom, I'll call this just y, and it's equal to negative 20 meters. So that's assuming that this tree is a pretty tall tree, about 60 feet tall, about 20 meters. All right, we know its initial velocity. Its initial velocity is equal to 0 meters per second. And we know its acceleration in the y direction is negative 9.8 meters per second squared. And what I want to know is, first of all, what is the time? And then also, what is the final velocity equal to at the bottom? Whenever you have these free fall problems, if the time's not given, you're going to want to find the time first. So I'm going to write my two kinematics equations up here. I have v equal v0 plus at, and then y equals v0 t plus 1/2 at squared. Now in both of these, v0 of course goes to 0, so this whole term goes away. And now I first just want to find the time. So I don't know v, I don't know this, but I do know y, and I know a, so I can find t. So I'm going to first now solve for y. So I'm going to put in 20 meters, actually negative 20 meters, equals 1/2 of negative 9.8 times t squared. So then t becomes the square root of 20 divided by 4.9. Let's see, if you didn't get that, I'll go back and do the steps part. We're just going to divide both sides by 1/2 of minus 9.8. And 1/2 of minus 9.8 is 4.9, negative 4.9. This gets rid of this side. I take the square root of both sides, get rid of these negative signs, they become positive. And then I can find the time is 2 seconds. All right, so the time to drop from the tree all the way down to the ground is 2 seconds. Now that I have that, I can find the final velocity. And the final velocity is just going to be v0 plus at. Of course, v0 goes to 0, and so this is minus 9.8 meters per second squared times 2 seconds, which gives me 20 meters per second. That is my final velocity. So I have this object that's dropping a certain distance. I first have to find the time, and then I can find the velocity. Time of 2 seconds and a velocity of 20 meters per second. Now, in the second instance, I have this flying squirrel. This is a flying squirrel, and we find that he drops a certain distance. Now, in this case, the free fall isn't in slow motion, so we can actually look at the clip, and you can go back now and see if you like. But we find that the squirrel is in motion just from looking at the clip for a time of 4 seconds. So I have this time of 4 seconds. I have an initial velocity equal to 0 meters per second. I have an acceleration in the y direction equals to minus 9.8 meters per second squared. And then I also have, well, I want to know what y is. And I want to know what its speed is at the bottom. And then we can look at how they relate to the previous problem. So notice that he's in the air for twice the amount of time as the peach falls through the air. So twice the amount of time. So we might think that, well, he'll have fallen from twice the distance and have twice the velocity. So we'll see. This was a considerably easier problem. If I want to find y, I have everything I need. I just say v naught t. It's 1/2 at squared. It's equal to 0 plus 1/2 of a is minus 4.9 times 4 squared. And that is equal to, I'll just round it off to 1 sig fig. 16 times 5 is 80, negative 80 meters. So notice that the time is increased by a factor of 2, and the distance has increased from the peach to the squirrel by a factor of 4. We've done this before, but it's fairly important. Look, if I have a function like this, y equal 1/2 at squared, if I double t, that's going to quadruple y, because t is squared and 2 squared is 4. And that's what I've done here. I've doubled the time, and that quadruples the distance. Let's see if it does the same thing to the velocity. Velocity is equal to v naught plus at. V naught is 0. So my final velocity is just going to be minus 9.8 times t, which was 4 seconds, 40 meters per second. Now, thinking in a similar way as we did before, here we have doubled our time from the previous problem. In the previous problem, we just had 2 seconds, and now we have 4 seconds, and we've doubled our velocity because we have a linear relationship between velocity and time, whereas there is a quadratic relationship between position and time. Let's stop there, and then we'll do this word problem in the next screencast.